Today I want to look at the next problem we'll be considering. Suppose that you're given numbers x0, x1, x2 out to xn, none of which are repeated, and function values to go with them, f of x0 through f of xn. I want to find some simple function, and right now by simple I mean easy to think about, easy to deal with, polynomial functions. I want to find a polynomial function that agrees with function f at x0, x1 out to xn at n+1 data points. For example, if you had only two data points, x0 f of x0 and x1 f of x1, obviously you can draw a straight line that connects the 2 points, so this certainly looks doable for 2 data points. If you have 3, the situation is seemingly more complicated. If all 3 points had the same y coordinates, the same function value, then obviously you could do this with a straight line, a horizontal straight line, in fact. If you had 3 points that lie on a straight line but is not horizontal, you can also obviously fit a straight line through those 3 data points. If you have 3 points in general, though, they won't be on a straight line. Looking at this situation, it certainly seems as though you ought to be able to do what we want to do, but the exact details are not clear right now. For each index k, which could be anything from 0 up to n, we're going to define a polynomial. We're going to find L n comma k of x to be the product of all x minus xi over xk minus xi, where I can be anything from 0 up to n, except we're going to omit the factor that has I equal to k. So this index is the index of productness here. This k and that k refer to which one of these L polynomials that we're going to talk about. If we included all factors, we would have a polynomial of degree n+1, since I could be 1, 2, 3 up to n, and also 0. By leaving that one factor out, we get polynomials of degree n exactly. Now, what's not obvious is what these things are good for. So in an effort to be transparent, I'm going to look at a specific situation where n is 2, meaning that the k can be anything from 0, 1, or 2 inclusive. And I want to write down these polynomials and see how they act. So L20 of x is the product of x minus xi over x0 minus xi, except I'm going to omit the one where I is 0. L21 of x is the product of all x minus xi over x1 minus xi, except I have to leave out the I equal 1 term. And similarly in this one, I have to leave out the I equal 2 term. If I didn't do that, we would be getting division by 0, and that would be no good. Thinking about L2 comma 0 of x, this is x minus x1 over x0 minus x1 times x minus x2 over x0 minus x2. These indexes always match. These indexes match. This index is which one of these polynomials I'm talking about. I want to evaluate this L2 comma 0 of x polynomial at the x values from my data set. So in the first one, I'm going to evaluate everything at x0. So replace this x and this x with x0 and write the result down. X0 minus x1 divided by itself times x0 minus x2 divided by itself. That would be 1 times 1, which is 1. If I plug in x1 into L2 comma 0, I get this, but one of the numerators is x1 minus x1. One of these factors is actually 0, so the product is 0. In L2 comma 0 evaluated at x2, here I'll have a factor in the numerator of x2 minus x2. That makes the entire product equal to 0. So in L2 comma 0, if I evaluate at x0, I get 1. And if I evaluate at any of the other data x values, I get 0. We will do the same for L2 comma 1 of x, which is this product. We leave out the I equal 1 factor. L2 comma 1 of x0, there will be a factor of 0 involved, so you get 0. L21 at x1, x1 minus x0 divided by itself, x1 minus x2 divided by itself. 1 times 1 is 1. And if you put x2 in, because of x2 minus x2 in the numerator, you end up with 0. And finally, looking at L2 comma 2 of x, which works out to be x minus x0 over x2 minus x0 times x minus x1 over x2 minus x1. If you evaluate at x0, you get 0. If you evaluate at x1, because of this, you also get 0. And if you evaluate at x2, you end up with 1 times 1, which is 1 once more. So the pattern here should be fairly obvious. This is a summary of everything we've figured out in the first half of the page. And even more symbolically, if you take L n comma k and evaluate it at x number j, what's going to happen to you is, if j and k are the same index, you get 1 for an answer. If j and k are not the same number, you get 0 for an answer. Those of you who already know some linear algebra, looking at this table of numbers will recognize it to be the identity matrix. We don't need to know that though. If you want to make this fancy, there's a symbol called the Kronecker delta, delta kj for instance, is a number that's equal to 1 if k and j are the same value and 0 if they're not. So a fancy way of summarizing our calculations here is that L n comma k evaluated at xj is going to be Kronecker delta kj. Each of these L polynomials, which by the way is named after Joseph Lagrange, in case you're wondering who to blame for all of this stuff, is a polynomial of degree exactly n. If you were to multiply such polynomials by numbers and then add or subtract them, there's no way for the power to get bigger than n, but because some terms could cancel out, it's conceivable that a product of constants times these Lagrange polynomials could be of degree less than n. That could happen. So any sum of constants times these Lagrange polynomials will be a polynomial of a degree no more than n. So where is this taking us? We're going to form a polynomial called p of x, and here's how we're going to do it. For each k from 0 to n, we're going to form the Lagrange polynomial. We're going to multiply that by a constant, by the function value that goes with x number k, and then we're going to add all of these things up. From what we've just said, this must be a polynomial of degree less than or equal to n, and the reason we're forming this polynomial in this fashion is it turns out to be the one that we're after. What I mean by that is, let's evaluate p of x, where x is going to be x number I, one of the x data values out of my data set. So take the preceding formula, and every place you had the variable x by itself, no index, replace that with x number I, and you'll find out that p at x number I is the sum k equals 0 to n, f at xk, L n comma k evaluated at xi. But we've figured out something about these Lagrange polynomials when evaluated at an x out of my data set. L n comma k evaluated at xi is Kronecker delta ik. This is a sum of a bunch of things. F of x0 times delta I0, f of x1 times delta I1, and so on and so forth. Almost all of those terms are 0 because the Kronecker delta is 0 for most pairs of indexes. The only time that you're going to get something different from 0 is when index k is equal to index I. So the only non-zero contribution you could conceivably have is going to be f at xi times Kronecker delta I. But remember, when the indexes are the same, the Kronecker delta is 1. So this is f at x number I times 1, which is f at x number I. The polynomial p has the property that when I stick x number I into it, where x number I is one of the x's from my data set, what comes out is the correct function value, f at x number I. So we'll say that p and f agree at x0, x1, x2, out to xn, or to use the fancier word, we say that this polynomial p interpolates f at the data points. So our suspicion turns out to be true. Give me n plus 1 data points with distinct x values. There is a way to find a polynomial that interpolates the data. There's a fact that you've probably heard mentioned before called the fundamental theorem of algebra. It says this: any non-zero polynomial with real coefficients can be written as a non-zero constant, an, times x minus r1 times x minus r2 out to x minus rn, where n is the degree of the polynomial. R1 through Rn are the roots of the polynomial. If real, they may be repeated. If complex, they have to occur in complex conjugate pairs. This was suspected to be true for a long time. I think it was proven first in the 18th century. For example, x cubed plus 2x squared plus x can obviously be written as x multiplied by x squared plus 2x plus 1, which in turn can be written as x times x plus 1 times x plus 1. If you wanted to be picky about it, you could write that as x minus 0 times x minus negative 1 times x minus negative 1. So we see that it's possible to write this as a product of a constant, 1 in this case, times x minus something else, x minus something else. The 0 would be root number 1, and root number 2 and root number 3 are the same number. We see 3 factors because we had a cubic. Another example of interest is x cubed plus x. Obviously, you can write that as x multiplied by x squared plus x. If all we know about are real numbers, we can't do anything more with the x squared plus x. But if we know about complex numbers, you can write that part as x plus I times x minus I, where I is square root of negative 1. Again, being picky, x minus 0 times x minus the negative of I times x minus I. So you see we have 3 linear factors, we have 3 roots, one of which is 0, and the other 2 occur in complex conjugate pairs. This polynomial that we have formed, based on the Lagrange polynomials, is a polynomial of degree no more than n, which interpolates the data that we're given, meaning when you plug in one of the xi's, the correct f of xi comes out. Suppose that q was another polynomial like that. By like that, I mean degree no more than n, and interpolates the data at the given data values. I want to form another thing. I want to form the quantity r of x equals p of x minus q of x. Since p and q are both polynomials of degree no more than n, r must be a polynomial of degree no more than n as well. However, if I take one of my data xi's and evaluate r at that point, I'll get r at xi is p at xi minus q at xi. Since both polynomials p and q interpolate my data set, though, p of xi is f of xi, and so is q of xi. That leads me to the conclusion that r of xi must be 0. And this is going to be true for I equals 0, 1, 2, 3 out to n. This leads us into an interesting situation. R is a polynomial of degree less than or equal to n, but R has at least n plus 1 zeros, if not more. The fundamental theorem of algebra, that is, said a non-zero polynomial had to have the given behavior. The only way out of this contradiction is to say that the R has to actually be the 0 polynomial. When I write this, I mean no matter what x is, when you put it into the R function, you get 0 for an answer. That means that the polynomial p of x minus the polynomial q of x is 0 no matter what x is, not just the x's out of the data set, for all x's. This means that p of x is the same as q of x. So what we've figured out now is this. Not only is there a polynomial of degree less than or equal to n, which will interpolate our data set, there's only one like that. there is exactly one polynomial of degree less than or equal to n that interpolates function f at x0 through xn. We may have various ways of writing this interpolating polynomial, but it's the same polynomial. We need to keep that in mind. That's not to say, though, that the p that we have found is the only polynomial that interpolates the data. P is the only polynomial of degree less than or equal to n that interpolates the data. I could imagine doing this. Let a of x be any polynomial and multiply it by x minus x0, x minus x1 out to x minus xn. This is going to be some other polynomial. If you were to evaluate that polynomial at one of the x numbers from the data set, say x number I, you would have a at xi times xi minus x0, xi minus x1, all the way down to xi minus xn. Xi is one of those numbers, x0, x1 out to xn. So one of these factors, at least, is going to be 0. So if I had any polynomial, a of x, multiplied by this quantity, then the resulting thing is 0 at each one of the xi's from our data set, meaning, though, that if I took p of x, which is a polynomial of degree no more than n, and this thing, which is a polynomial of degree greater than n, and add them together, this is still going to interpolate my data. It's just not going to have the minimal degree possible. Later on, we're going to take advantage of the fact that the polynomial of degree less than or equal to n that interpolates the data is not the only such interpolating polynomial, but it is the only interpolating polynomial of degree n or less. In our next discussion, we'll begin looking at how one would program these things, and it should be completely straightforward if you've been keeping up with the videos as we've gone along. I hope everyone's having a good day, and we will talk again soon.